we're finishing out our equilibrium stuff, I talked about solubility. We're working on a problem where we're looking at copper iodate, just kind of rushing through it at the end. So usually the way that these types of problems are set up, audio is really grainy. So, I wonder if it's using a different audio. Oh yeah, hold on.
What about now? For some reason, I won't let my earbuds work, but that's okay. You guys don't talk that much. I'll just hear it through my computer thing. Shouldn't be too bad of an echo. Yeah, you're welcome. Thank you guys for letting me know. It's like the one piece of advice I got from one of my friends who works in film was get good audio. Video and such is not that big of a deal, but shitty audio is terrible. So get a nice mic, or not a nice mic, but a decent mic. Okay, yeah. So we're looking at solubility, and we look at it just through this lens of equilibrium constants. Same thing we've been talking about. The main thing is just that when you're looking at solubility, the solid that you're dissolving is usually there in excess. And so it doesn't really matter how much solid you put into solution. And that's hard for me to explain why that's true. You kind of have to think about it. I guess it's not that hard. It's just that, like once you hit a point, so the equilibrium constant, sort of, it's a measure of how much copper and iodate are in solution in a sense. And at some point, once you get past saturation, these little rocky things I'm drawing at the bottom are the solid. Once you get past saturation, it doesn't matter how much you've added here, no more is going to go into solution. So it should make some intuitive sense that the amount of the solid that you have doesn't affect how much goes into solution once you get past that point. If you imagine making iced tea or something, or just, if you just imagine making iced tea, once you get past the point where you've added so much sugar that no more sugar will go into solution, you can keep adding more and more and more and more and more. The amount that's dissolved is going to be the same. And so even if that doesn't make perfect sense, it should make some sense that the amount of solid that you start with is not consequential. I don't know. It's not super intuitive. It helps if we're like actually doing like a lab or something to get experience with this stuff. Anyway, but the nice thing about that is it simplifies the equilibrium constant expression. So it's the same equilibrium constant expression that we've been working with. It's just that solids and liquids don't go into that expression. So when I write out my equilibrium expression for it, I get something that looks like this. And so if I want to solve this, so if I'm given KSP, so let's see, I'm given KSP, which I have written somewhere here. So KSP for this is, where is it, 1.4 times 10 to the minus 7th. So you've got this tiny KSP, which is pretty typical for these things. We can then go ahead and solve. We can solve for what we would like the solubility or the molar solubility, what we might call it, for this, without knowing anything about the amount that we're starting with, other than, we have enough of it to where we're past the saturation point. And so we can write out a Rice table here, make some space. This we just don't care about. This we're starting with none of it. The change is just going to be whatever dissolves, and they're going to be stoichiometrically, you know, related. So 2 times the amount of iodate that we have copper there. That's where the 2 in front of the X comes from. That should be kind of old hat to you guys at this point. And so we can write out an expression like this. Since we know the KSP, oops, I forgot my square there. Let's see, so we'd end up with 4x squared times x, so 4x cubed is equal to 1.4 times 10 to the minus 7th. Punch that into my calculator. So let's see, so we'd have x is equal to this number, it should be some really small number, divided by 4, and then we're taking the cube root of it. Is that right? It's like been so long since I've done, I'm gonna have to use Google for this. I'm gonna use my damn calculator to take the cube root. Actually, somebody just tell me in the damn chat window what the answer is, if you're working along. If not, I'll get an answer in a second. Thank you. Jesus. Okay. So anyway, so we end up with this number x. So interpreting x for this is now sort of our plight. Let's see. So x in this case, the way you would express this, all right, so x, so yeah, so look. So you want to express x, it's kind of, so the amount of copper that dissolves is equivalent in terms of molar stoichiometry to the amount of copper iodate that is soluble. It's a really obtuse way to say that. Basically what this number is, 3.3 times 10 to the minus 3 moles per liter. That's the amount, if we go back up and we see what we're solving for here, so we solve for x. If we go back up here and look at what we're solving for, it's the amount of these things that are dissolved in solution. And so when we express what the solubility is, because that's what the overall question for this was, you know, what is the solubility of copper iodate? And the answer is, the way that we would express it is you want to express it in terms of whatever is equivalent stoichiometrically to this. So 0.00327 moles of this amount, 0.00327 or 3.3 times 10 to the minus 3 moles per liter is the solubility of this substance over here. Because for every mole of this, you get a mole of this in solution. You know, so if you have 3.3 times 10 to the minus 3 moles of this in solution, that means that that much of this has dissolved in terms of moles. So that would be sort of how you would express the solubility there. So this is, you know, the general workflow for this. It's in terms of solving, in terms of just solving the problem, it's much easier, I think, than like the acid-base equilibria stuff. You know, we're not dealing with the neutralization reaction, although we could probably set this up to get a little bit ugly. And when you're solving this, the equation is pretty straightforward. But interpreting exactly what this means and kind of relating it back and sort of getting a handle on what I'm talking about here, where it's like, it doesn't matter how much of this you have in solution. That can take a little while to build sort of a model of that in your brain. So just, I think when you're solving these, perfectly acceptable, probably the right thing to do is first kind of get a workflow for how to solve it. But if you can, spend some time just thinking about what the hell's going on there at the end. You know, what do those numbers mean? Yeah, let's see, how much more depth do we want to get into? I think we're probably good to stop there. Let's see, KSP. Let's talk about the common ion effect really quick. I guess we can talk about precipitation. I don't want to spend too much time on this stuff. We're kind of familiar with the common ion effect. So it's just this idea that falls out of Le Chatelier's principle. So let's just look at a different one. So if we're looking at something like calcium sulfate, and we're looking at the equilibria there. So this is a solid and these things are aqueous. If I do, let's say I have two different experiments. So this is my calcium sulfate here, you know, chunk of white stuff or gray, whatever. And let's say I have two solutions. So you have solution A and solution B or whatever. But in solution B, let's say I have calcium already dissolved. So let me actually write it over here. Let's say this is 1 molar calcium. Calcium, I don't know, chloride, something that's soluble. I'm going to get rid of the anion, but naturally there's an anion there because charges have to be balanced. But over here I have pure water. And I take the same amount of calcium sulfate and I dissolve it in each of them, or I put it in both of this. So I put that in there, I put that in there, let it sink to the bottom. Which one is it going to be more soluble in? Sort of the question. Or are they going to be equally soluble? Does the fact that this has calcium already dissolved in it matter? Yes. Yeah, very good. The answer is yes, and it's because of this idea of Le Chatelier's principle, which is that for example, if you imagine the way we normally talk about Le Chatelier's principle is if you were to add the product after the reaction has come to equilibrium. And you can think about it in the same way, in that kind of same way here. But if we have one of the products present, it's going to push the equilibrium back towards the reactants. It's getting really messy. But yeah, if I have one of these present in solution, it's going to push the equilibrium back towards the reactant side. So the common ion effect is just that if you're trying to dissolve something and you have one of the ions from the salt in solution, it's going to be less soluble. So it's, you know, you're going to get less calcium sulfate dissolving in B. And so this is the common ion effect. You know, it's related to Le Chatelier's principle. It also falls directly out of the equilibrium expression. So I feel like I say this a lot. I'm not sure that it really gets across because, you know, there's a lot of crap going on that you're trying to learn all at once. But again, if we think of the equilibrium constant for what it is, which is a constant, it tells us, the equilibrium constant tells us what the multiple is of the calcium concentration sulfate concentration that you can have in solution. So K, in a sense, for, at least for solubility, it's the limit of how much calcium, for example, if you had it in here, it tells you exactly how much calcium you can have in solution. So if you're just dissolving a chunk of calcium sulfate in a solution, yeah, you're going to have one of these and one of these for every calcium you have. But really, if you look at this expression, it's a little bit more powerful than that. It says it doesn't matter how much sulfate and calcium you have there, as long as when you multiply those two, so as long as when I multiply the sulfate concentration times the calcium concentration, it comes out to be KSP, whatever KSP is equal to for calcium sulfate, 6.1 times 10 to the minus fifth. So at room temperature, at least, this number is immutable. But calcium and sulfate could be different. So if I have a very high concentration of calcium in solution, which is what's going on here, that means the amount of sulfate that can be dissolved is very, very small. And that, because of that, that means that the amount of calcium sulfate that can go in a solution is going to be very small. So all of these kind of names and stuff that we have, common ion effect, Le Chatelier's principle, etc., they all come out of the same idea here, which is just that K is constant. So if I change something over here on this side of this equation, all the other variables have to adjust such that this statement is still true. So if this is constant and I change the calcium concentration, let's say I increase it, so if this is increased, that means that the sulfate concentration that's dissolved in solution will decrease. Just as one last example before we move on to something else. So there's a little bit more stuff in the solubility chapter. I think you guys will be okay. Like in the precipitation part, in Q and KSP, we could go over that. But I mean, I really just want to get to kinetics. Let's see, I'll just make this last point. I feel like you guys must be tired of equilibrium constants at this point. All right, so if I have a 1 molar solution of sodium cation and I dissolve calcium sulfate in it, so same kind of experiment, just for consistency's sake. So if I'm doing the same kind of experiment down here, goodness, perfect. I feel like I'll leave it there. All right, if I'm doing the same kind of experiment here, let's say solution C, you would expect it to be calcium sulfate is equally soluble in sodium chloride as it is in pure water. Because the common ion effect works through this idea, right? If you look at the KSP, it has calcium, it has sulfate that appears in it. If I add sodium chloride, it doesn't affect anything on this side of the equation. So if the solution is following this sort of idealized situation thermodynamically, then you don't expect sodium chloride to change how the calcium sulfate dissolves at all. So it only matters, the common ion effect is only when the ion is common to the solid that you're starting with. So either calcium or sulfate or whatever your solid ends up being. So that is how solubility works. Okay. All right, and I really don't want to spend. Now let's just we're gonna get on the kinetics because we're never gonna. And if we have to cut something, we'll cut out solubility stuff. Okay, so there's really two like physics type things that we're worried about, practically speaking, for chemistry. The first is this idea of thermodynamics, um, which is what we've been talking about, which is, I start with some amount of A, let's say, so I'm just writing out a generic reaction here. Um, and let's say it just spontaneously converts itself into B. So real simple reaction here. What we've been talking about is equilibria, which is only concerned with, we look at a reaction diagram, it's concerned with where I'm starting, let's say we get whatever free energy or something over here and our reaction coordinate down here. It's only concerned with here and here. So I start out at A and I end up with B, and there's some free energy associated with that. And that's really what we're talking about when we talk about equilibria. So we're talking about the change as you go from A to B. We're not talking about how you get between those 2 points. Kinetics is concerned with the path. So let's say, let's just say, I'm going to say, I think this is correct. I don't know if it's precisely correct, but in thermodynamics, usually what you're concerned about is the initial state of the system and the final state. But you ignore everything else in between. You say, okay, what's the free energy of the product? What's the free energy of the reactant? In kinetics, and I'll draw this back to an analogy that, is a little less abstract. Kinetics, this is the path between the initial and final state. So to draw an analogy, between like a map, like thermodynamics would be concerned with, like I'm at my apartment now. If I drove to UT, so it's like I'm here at my apartment, and then UT is over here. That's my illustration of the tower. It's got a clock or something on it, right? Maybe some some of you guys haven't even been on campus very much, but they have the bells sound really weird a lot of the time. Am I the only one who feels that way? I feel like the bell music that they play sometimes is like really wonky sounding. Anyway, so thermodynamics is concerned with I'm here and then I'm here, right? It doesn't care about how I get there. Kinetics is like how I get between my apartment and UT. So if I get in my car and I get lost and get on like Mopac going north for like 2 or 3 hours and then turn back around and come back to UT, that's what kinetics is. So kinetics is concerned with the time it takes to go between 2 states, whereas thermodynamics is just concerned with the initial and final state. So this would be like the initial state, and this would be the final, and this would be whatever kind of path I take. So if I go to map, if you were looking at this, like starting point, apartment, this is probably a better way to draw this. We got UT over here. Kinetics would be concerned with, do I take this path to get there versus, if I'm drunk, which I would never drive drunk, obviously, but, if I take that path, those are all going to take different times to get there. If I want to get real crazy and just drive all around for a while before I get in, those are all different paths. That's what kinetics is concerned with. Whereas Thermo, all we ever talk about is like, okay, I started here and I ended up here. That's all it's concerned about. So in a reaction coordinate diagram, when we look at kinetics, when we connect these two states, so here's the free energy over here, the change in free energy. When you're looking at the path between them, we draw a line that looks like this. And so this barrier here, the activation energy or whatever, is related to the kinetic aspects of the reaction. It's the amount of energy that needs to kind of be put into the system to get it over this barrier, and it's related to how long it's going to take for the reaction to go. So that's the kind of the missing piece here that we haven't talked about. Yeah, another good thing to think about for this is, if you've got, it's hard because it's like, I don't know how much physics you've taken, but if you've got like a, let's say you've got a little like weight or something right here on the side of a ledge, and this is, the ground. This is like top of a desk. It's a weird looking weight. You get the idea. Thermodynamics is concerned, like if I throw this onto the ground, let's see, initial state, let's say, and that's the final state. Thermodynamics is only concerned with where I started. So like, whatever the height is here. And the final height down here. It's like height 1 and height 2. It doesn't matter in thermodynamics if the path that this thing took off the desk was, to just fall directly down like that, or if I were to take it and do some kind of, throw it way up in the air and then let it go down. All thermodynamics is concerned with, it's just saying that, the potential energy here is one measurement, and the potential energy when it hits the bottom is a different measurement. How it gets there doesn't really matter. But practically speaking, that makes a big difference in terms of like, if you're a chemical engineer or something and you're designing a reactor, the amount of time it takes to get between the initial state and the final state is really important. If the time scale is 10 years for you to have a reaction go to completion, that's not very practical. So kinetics are a really important aspect of chemistry. Okay, so let's take a look at what we can do with these things mathematically, because that's where we're headed. So if you're looking at a reaction, I'll use this one's on the GChem website. They usually try to give different examples, but I like this reaction a lot. So if you're looking at the Haber reaction for making ammonia, so if you've eaten anything today, the nitrogen in it was probably produced via this reaction. We can talk about the rate of the reaction in terms of changes in the concentrations. So you can imagine that if I were to say, so the thought experiment you can do to try to wrap your head around this is, if I were to say, like, monitor this reaction to completion, even not having any experience, what would you do? You'd go and you'd either look at the amount of product formed, so you'd say, okay, the concentration of ammonia is increasing. That's how I would monitor whether the reaction was finished or how far along it was, or monitor how fast nitrogen or hydrogen is disappearing. It's the common sense way to kind of measure it. When we express this, in terms of rates, we could express it as the change in the concentration, so D, you know, in terms of like the little delta from calculus or whatever, just means change. So the change in nitrogen concentration with respect to time, that's what we're looking at here. And then we don't have to just monitor nitrogen. We could also monitor the change in, let's say, the hydrogen gas concentration if we wanted to. It's important to note, though, that the stoichiometry will play a role here. So the change in the nitrogen concentration is going to be different from the change in the hydrogen concentration because the molar ratio, the stoichiometry here is 1 to 3. So the hydrogen concentration is going to change a third as fast as the nitrogen. And then you can look at the ammonia concentration as well. And that's going to have a 2. And then naturally, if you're looking at the change in nitrogen concentration, that's going to be decreasing, so we put a negative sign here, whereas this is going to be increasing, so we put a positive sign there. Just like when we look at equilibria and stuff, we look at, you know, we kind of connect everything through X, and we use the minus and plus in the stoichiometry to relate it. The same thing is true of rates, only now instead of looking at just what the final concentration is, we're putting this extra little bit on here. We're saying, well, this is how it's going to change. This is looking at it at any instant in time instead of just at the end of the reaction. And so this is what the rate of the reaction is. It's just how you measure rates of reactions. It's an intuitive way to measure them. It's not any different from looking at other rates that you're more familiar with, like typically what you're thinking about when you take physics or something, you're thinking about position. You know, how does your position change with respect to time, which is essentially the velocity? It's the same idea. So, you know, if I were to say dx dt, that would be an expression of like how fast it takes me to go between, you know, if we go back to this example up here, dx dt would describe this, you know, how does my position change with time as I approach ut, which is, you know, velocity or whatever. Here we're looking at just concentration instead of position because we're dealing with chemicals, and that's what chemistry, you know, that's what we measure chemical reactions in terms of its concentration. Okay, so what can we do with this? So yeah, this is where things get a little bit wonky. So not wonky, but a little bit confusing, I think, a lot of times for students. One second. Okay, so for a particular reaction, we can define its rate. That's what we just kind of did. So in a reaction that you write, you can basically write out its rate in this way. So, you know, that you can imagine in a generic reaction, A plus B going to C, you can write out this exact expression down here and just sort of map, you know, this to here, and just make sure that the signs, so if it's over here on the product side, your sign is going to be negative. And if it's on the if it's on the reactant side, your sign is going to be negative. If it's on the product side, your sign is going to be positive. Okay. So in thermo, like when we're talking about equilibrium, we're all about equilibrium constants. What does K equal? And that's kind of how we're solving things. For kinetics, which is what we're looking at now, we're going to look at rate laws. They have their own constants associated with them. So for a particular reaction, let's say we are looking at this reaction. So let's say you've got ammonium and you're reacting it with the nitrite ion. That is going to form nitrogen gas. Oops. In water. We want to describe the rate for this. So we can describe the rate like we did up here, right? And say that the change in nitrogen with respect to time, et cetera. But we can write another expression called the rate law. Which says that the rate is going to be dependent on the concentration of ammonium and the concentration of nitrite that we have in solution, raised to, this is where things get a little bit confusing for students. I'll call this X and Y actually. Raised to some power X and some power Y. So for the equilibrium constant, this is, if you're tuned out, pay attention to this one piece. For the equilibrium constant, right, if we were writing K for this, the coefficients that are out front of the compounds inside of the reaction, so 1 and 1 here, would go into this part of the equilibrium expression. That is not true for rate constants. For rate constants, at least when you're looking at the overall reaction, these exponents are kind of unknown and have to be determined empirically. So I'm going to write that out. We don't know what X and Y equal unless we do some kind of experiment. Actually, let me put that in a little more understood. We don't know what X and Y equal just from looking at the overall equation. So what is this expression telling me? If we kind of step back for a second. So we've got this way of expressing the rate over here that's sort of somewhat intuitive, which is just saying that, you know, whatever the rate is. So if we were to write one down here for this one, we could say something like, we could also say that the rate was equal to the change in the ammonium concentration with respect to time. This is one way to express the rate. But we also have this rate law, which tells us that the rate is going to be dependent on the concentration of the reactants raised to some power, multiplied times some proportionality constant. So the way to kind of think about, like, why did that even make sense? So this is like, I'm trying to follow the rate. I'm going to look at the changing concentration. This is telling me that this rate is equal to this expression over here. And so the reason that this expression works is because it's sort of an expression of the probability of ammonium bumping into a nitrite ion, so these are our reactants, in a way that's productive that can produce nitrogen gas and water. So if you're imagining sort of mixing these two things up in a big reactor, this expression sort of takes into account, or it sort of is an expression of what's the probability of having this bump into this and having it be productive and actually make a product there. And so unlike with thermodynamics, where we don't really care about the path, which is why we can kind of express what this isn't like without having to know anything about the path, just by looking at the overall equation, we are concerned with the path here. So if we wanted to figure that out, we can use what's called the method of initial rates. So one last thing here is K, so this K here, little k, different from the equilibrium constant. This is the rate constant, which again is an empiric, just like the equilibrium constant in this sense, is an empirically determined thing. It's a proportionality constant. That is correct. Yeah. So if you think about it, the rate, which you might expect, is going to be proportional to the concentration of ammonia times the concentration of nitrite, both of these raised to some power. And so if anything's proportional, we can get rid of that proportionality thing by putting a constant out front. That's what K is. Okay. So we don't know what X and Y are here. We don't know what those are, so we have to figure those out. And so one type of problem that you'll see in this chapter is where you're asked to figure out what the order of the reaction is, which is asking you what X and Y are essentially. So you'll be given a table like this. And so this little knot down here just means initial. So those are the initial concentrations of ammonia and nitrite that you start out in solution. And then you're given different concentrations. So So what you're doing here in this experiment, like if you were actually running this, is you're doing exactly what you would naturally figure out, even if it doesn't feel that way right now, because you're like, I don't know what the hell's going on, because there's all this crap everywhere. But you're doing, this is how you would naturally kind of figure it out. So you would ask yourself the question, even if you were kind of stepping back from this quantitatively, if I were to ask you, you know, what effect, if we were looking at this reaction, we're looking at this reaction here. Let's bring it back down here. If we're looking at this reaction here, and you were asked, you know, what effect does ammonium have on the rate of the reaction, like how fast it goes to completion, what you would do is you would change the concentration of ammonium, right? You'd say, well, I'm running it at 0.1 molar. What happens if I double the concentration of ammonium? How does that affect the rate? That's the exact experiment you do, and that's what we're doing right now. That's what these experiments are about. So you'll note here For ammonium, between experiment 1 and experiment 3, I've doubled that. Let me actually, sorry, between experiment 2 and experiment 3, I've doubled that. But for experiment 2 and experiment 3, I kept the nitrite constant. So I've isolated out the effect of the ammonium concentration on my rate over here. And what do I see happen? So when I take 0.1 and I double it to 0.2, 2.7, and now it's 5.4 times 10 to the minus 7th. I see that my rate increases. And then I can look at what happens in the same situation. So here I have nitrite. Here, if I look between, run out of colors here. Let's see, actually, I think I'll do this. So if I look between experiment 2, yeah, if I look at experiment 2 and experiment 1 here, I've halved the concentration of nitrite. But if I come over here and I look at my concentration of ammonium, that has stayed constant. So then now I'm isolating out what's happening. Oh, damn it. Now I'm isolating out what happens when I change the concentration of nitrite. And so as I go from here to here, right, I've halved the concentration of nitrite. I've kept this constant, so I've isolated that out. I can see that the rate decreases. Right? And here it's very obvious that it decreases by exactly 1/2. Oh yeah, the units for the initial rate, let's see for this one. It's moles per liter second. You can get the units out of the rate constant expression that we have up top if you need them. But generally, that's my bad not giving them to you. But anyway, using this, we can figure out, so what we're trying to figure out is what is the effect of the changing concentration on the rate there? That is what allows us to solve for X and Y in this rate expression. Right. I don't want to rush through this calculation. It's a reasonably straightforward calculation now. Yeah, we'll talk about this. So from this data, though, we can derive what X and Y are equal to. If you want to kind of get ahead on that, you can go and look at, it looks like the GChem website has a solid explanation of this. But the main thing to take away, I guess, from today is like, one, what the hell are kinetics? Kinetics is looking at the path between here and here, as opposed to just like what happens at the beginning, what happens at the end. And two is, one, we're going to describe this. Ultimately, we're going to integrate this rate law. But we can describe the rate by just looking at the concentrations, by taking the multiple of the concentrations of the reactant and raising them to some power and multiplying them times a proportionality constant. But in order to get this, and this is it's a minor thing that I keep saying, like it's a sidebar kind of thing, because it's not, I don't know, it's not like part of this like big overarching goal, but it's a thing that's super confusing for students is X and Y and all of these different types of things have to be determined empirically. That's why we have all this experimental data down here. So remember, if you go back and look at your equilibrium notes, we want to know what those powers are for equilibrium. We just take the coefficients and we just plug them in there. This is rates. Oh, is it due on Friday? I'm sorry, guys. Yeah, I can do that. That's an accident on my part. But if we just look at these, what was I saying? Yeah, in order to figure these out, it's not related to these coefficients directly. We need some sort of experimental data to do it. And that's what we're trying to figure out here. And so we'll go through this and then we'll go into integrated rate laws and stuff like that. The timeline for this material gets a little bit compressed because we have Thanksgiving break and stuff. And I let equilibria kind of lag because I didn't want to put that on top of acid-base chemistry. But we'll get through it. Or we can always punt on it if we need to move some stuff, but I think we'll get through it. The kinetic stuff, even though it seems confusing, when you actually get into the problem solving of it, it's not as bad. So if you're confused, I think that conceptually it's a little bit more confusing, but mathematically it turns out to be a little bit easier. I think students struggle a little bit less with this material. Anyway, all right, let's pick up on this on Friday, and I'll talk to you guys in a minute in office hours. Thank you guys. Okay, good. Thank you. All right, let me check out for 1 second here.